here we are with the second part of neural networks. In the first part, we left off at gradient descent. So we will pick up from that only. So is my screen visible? Can anybody say if my screen is visible or not? Okay. So we will start off with gradient descent again, where we ended the last session. So, what is gradient descent? First of all, in machine learning, gradient descent is an optimization algorithm which is commonly used to train the machine learning models and the neural networks. So, what do you understand by this statement? What is the basic principle behind machine learning? In machine learning, we predict outputs to some inputs after training. So in this training, what do we actually do? We have some inputs and we have some outputs which are known to those inputs. And then we have to build a model which can predict the outputs as close as possible to the actual outputs. So here is where gradient descent comes. So to predict the function for which we want to build a model, we have to have some optimization algorithm. Why? Because when we start off with building the model, obviously the results would be pretty much with error. Why? Because in the starting, the machine doesn't know anything about the model. In the starting, the machine doesn't really know what to predict, what sort of inputs to expect, what sort of outputs to give. Such things the machine doesn't know. So here is where the gradient descent comes. So for the gradient descent algorithm to work, the function that it will be predicting should be differentiable and convex. So these are some properties that we all ought to know from our basic mathematics course. I guess we all know what a differentiable function is and what a convex function is. Do we? Hello guys. Do we know what the differentiation, what a differentiable function and a convex function is? Okay. So why should it be that the function should be differentiable and convex? We will address this question a little bit later. First, we ought to know what the gradient descent algorithm will work on. So this is here, you know the cost function. I guess you know what the cost function is. The cost function is what helps us to give the error margin while training. Here, the yi in the cost function is the actual output which will show with the given input, and the h of theta I is the predicted output that the model will predict. So here, this is a cost function called the mean squared error function. You can see why this is called the mean squared error function. The error is h of theta I minus yi. It is squared and then it is divided by m with a constant factor of 2. Now, why this constant factor of 2 comes? This is because of the gradient descent algorithm. While because this while we perform the gradient descent operation, this 2 will get cancelled during the differentiation function. So this cost function is basically what we call the mean squared error function. So the gradient in the gradient descent algorithm, first we compute the gradient of the function with respect to these parameters that we call theta. So what are these parameters theta? Theta are the parameters which we are going to train, which the model will actually learn. This is where the machine will actually learn. What is the machine actually learning in this model or in this training process? The model is actually learning these parameters theta. So these parameters, once we start training, we set off with some given set of parameters. We don't know whether they are correct or wrong. They will most probably be incorrect. So our objective is to improve upon those parameters so that those parameters get more and more correct, so that we can get a function which will most accurately predict the outputs with the given inputs. In the gradient descent algorithm, this is the first part that we do. We find the gradient. We find the gradient with respect to the parameters. We find the gradient with respect to the parameters because it is the parameters that we want to change. So we are keeping it as the variable. This theta is actually a matrix representation of all the parameters in the model. In machine learning or in general in linear algebra, we find it comfortable to work with matrix algebra because in matrix algebra things get compactly written down, and it helps in a lot of ways, like performing these gradient operations or some other operations like vectorizations, etc. So in the gradient descent algorithm, the main thing is to change the weight matrix or the set of weight parameters so that our model can predict the output function most accurately. So how do we do that? In this algorithm, we iteratively calculate the next point starting from a given point using this gradient at the current position. Then we scale it by a factor which we show here as the constant. This is called the learning rate. And then we subtract this value obtained from the current position or the current set of weights. This makes one step. And this is how we get the next set of weights. So why is this algorithm called gradient descent? Because we strive to find the minimum of the cost function. You see here, this is how the cost function looks for two parameters theta 0 and theta 1. The cost function j of parameters theta 0 and theta 1 looks like this. Now this is something that is visualizable because there are only two parameters theta 0 and theta 1, and the cost function depends only on these two parameters. So it is possible to represent this graph in a 3D plane or in a 3D space actually. If the number of parameters goes upwards of 2, then it actually won't be possible to visualize this cost function theta 0, visualize this cost function theta, which depends on parameters which are more than 2. Because then if suppose there are 3 parameters, then we will need a 4D space, or if there are 4 parameters, we will need a 5D space, and our brain cannot process 4D or 5D or more than those spaces. Can you guys catch up with me till now? Hello? Do you guys have any doubt till now? Okay, I guess not. Okay. What is h of theta? H of theta is the predicted output. H of theta is the value that our model will predict. Here you see. In this picture, in this slide, you can see here h of theta x is the predicted value. This is the value that our model will predict. Theta is the set of parameters of the model, and h of theta is what the model will predict, or this is what the model actually predicts. Okay. So here you can see this is the cost function, which depends on only two parameters, theta 0 and theta 1. As I had shown earlier, this cost function is called the mean square error cost function. There are other types of cost functions as well. This is what we call the gradient descent algorithm. This subscript j here that you see refers to individual parameters of theta, of the set theta. Here alpha is the learning rate. In the gradient descent algorithm, we differentiate partially, that is the del function, we differentiate partially with respect to each of the parameters that are in the model. So if there are more than two parameters also, then the number of parameters will be given by j. So here in this part, you can see it is illustrated here, though this will probably be a bit mathematical, so you don't need to worry if you don't understand. This is how the gradient descent algorithm works. I mean, this is how the partial differentiation is done. So here you can see why this factor of half had been introduced. When we differentiate partially with respect to theta, this square term, the index of this square term comes to the front and it gets cancelled. So this actually helps to simplify things a bit. So that is the main motive of introducing this half term in the cost function. There is no other motive. And please do note that here there should be a summation sign. It is not given here. It is a mistake. over here. Here, where I'm pointing my cursor, there should be a summation sign, summation over I from I equals to 1 to m. So even if you don't understand this differentiation part now, it won't really matter much. What I need you to know is this is what essentially the gradient descent algorithm is. And the constant that we see here is what we call the learning rate. The learning rate is actually the length of the step that should be taken downwards this hill. In this picture, as you can see the points are marked by some crosses, and the length of each stride between these points actually gives a measure of the learning rate. The learning rate shouldn't ideally be the same for each step. Let me show you some simulations regarding this. This is the first simulation that I'm trying to show. You can see that this function is differentiable and it is convex, like convex upwards. So this function has a minimum. So we can be sure that in this model we will find the minimum, that we can find the minimum of the cost function. So here we start off from the point 0, and then we make a comparative study of two learning rates, one with a learning rate of 0.1 and one with a learning rate of 0.8. So in the graph towards the right, the learning rate is 8 times that of the graph towards the left. So we start off at 0, and you see the length of the stride from point 0 to 1 is not the same in the two graphs. Similarly, from 1 to 2, it is not the same in the two graphs. None of the strides in the two graphs is the same. But the fact here to notice is that since this cost function is very simple, it is very intuitive to see that this will converge at the point 2 on the x-axis. So if you go with a larger learning rate, it won't affect much till a point. Now we will see how much the learning rate actually impacts this gradient descent algorithm. So here is one other diagram, a comparative sort of diagram with 4 graphs. Here also it is the same cost function. It has a minimum at around the point 2, and we are making a comparative study with 4 different learning rates. The first one being with a learning rate of 0.1, the second one with 0.3, the third one with 0.8, and the fourth one with 0.9. In the first one, you can see that it takes 24 iterations to reach the minimum. In the second one, it takes 8 iterations to reach the minimum. In the third case, it takes 15 iterations to reach the minimum. And in the fourth case, it takes 33 iterations to reach the minimum. So what are the things that we can conclude from this comparative study? Can anybody tell me? What are the things that we can conclude from this comparative study? There are 4 different learning rates with increasing from left to right, but the number of iterations are different. The result is almost the same. It is very much close to 0. So we need not worry about the result. In the first case, the iterations we require are 24. In the second case, we require 8. In the third case, we require 15. And in the fourth case, we require 33. Can anybody tell me what conclusion can we draw from this comparative study? Okay. Okay, I'll just say that. Here, you see, in the first case, you see, in the beginning, the strides are big. It's quite big. So in the first iteration, we take a step from around 47 to around 28. In the next step, we go to around 18. In the third step, we go to 10. In the fourth step, we go to around 6. And from that onwards, the number of steps taken is really very small. Why is this? This is because as the function approaches the minimum, the value of the gradient gradually slows down. Here, the learning rate is constant. The learning rate is not really changing. We have kept the learning rate fixed at 0.1. But as we go down from one iteration to two iteration to iteration number 3, 4, 5, we can see that the gradient of this function is lowering. So as we approach the minimum, the gradient is also decreasing. So till the result is reached, it will take around 24 iterations. So what happens when we make the learning rate 3 times? We see that the number of iterations taken is 8. The first step is quite big, and the second step is quite small compared to the first step. Now, why is that again? Obviously, the gradient at this point near around 9 is much greater than the gradient at 5. So obviously, the step to be taken at the point 5 is much lower in value than the step to be taken at this point. In the third case, you see that in the first iteration itself, we overshoot the minimum. In the second iteration, we overshoot the minimum yet again. And like this happens, and finally, it takes around 15 iterations to reach the minimum. And in the fourth step, in the fourth case, it takes 33 iterations. We are constantly shooting down towards the other side. Since the learning rate is this big, with even a small magnitude of the gradient, the actual length of the step taken is quite big. So in every iteration, we actually overshoot the minimum by a large margin. So here, the thing to notice is that it is not generalizable that with a simple, that even with a simple curve like this, if we go on increasing the learning rate, it is not true that we will get to the minimum faster. In the first transition, when we are transitioning from point 1 to point 3, we see that the number of iterations go down by a factor of 3. But when we are making a transition from a learning rate of 0.3 to 0.8, the number of iterations is increasing. And when we are transitioning from 0.8 to 0.9, the number of iterations has more than doubled. Here also, in the second transition, the learning rate has been more than twice. It has gone from zero point 0.3 to 0.8. So we can say 0.8 is more than twice that of 0.3, and the number of iterations has gone around twice. But when we are transitioning from 0.8 to 0.9, it is nowhere near twice of 0.8. I mean, 0.9 is nowhere twice of 0.8. But still, the number of iterations has gone over twice. So the lesson to be taken from this comparative study is that it is not really predictable on how to choose the learning rate. We have to go on experimenting with different learning rates and see which one works fine, or rather which one works the best. And the thing is that here this function is very much simple. This is a very simple and intuitive function. But in real life machine learning models, we actually don't know what the function will look like, and it may happen that the function may actually be very much complicated. So there's really no way to figure out what the learning rate should be. So is it clear till now? No, we cannot really comment on the fact that with a higher value of learning rate, there's a higher probability of missing the minima, because you see, it actually depends on the function itself. Here we have a very simple function. This function or this function is a very simple function. So in the first case, we have nearly tripled the learning rate, and we see that the number of iterations go down by a factor of 3. But this is certainly not the case with the second or the third transition. So this depends on the function itself. And as with real life machine learning models, we do not really know what the function will be like. So we do not really, I mean, we cannot really comment on the fact that what the learning rate should be. We can only experiment with different learning rates and see what the best one is. Any more questions? Okay. No, there is no specific name to this function. As I have said, this is the cost function that we are trying to calculate the gradient on. This function does not have any specific name. This is just a very simple function that we are using as an example. But the functions may be quite different, and the functions may be quite difficult to interpret. Okay, so carrying on with the learning rate thing again. Here we have a function. You can see this function is not as sweet as the previous one. You can see that here there is some sort of a saddle point at around x equals to 0.1 or 0.2, and the minimum of the function lies at around x equals to 1.5. So we start off at the point 0 with a learning rate of 0.4. Sorry, we start off at x equals to minus 0.5, which we denote here as 0. Here 0 means 0 iterations. So in the first iteration, we take a big step and we overshoot this saddle point. After that, in step 2 and step 3, we gradually move towards the global minimum. But in step 4, we overshoot the minimum. And from that onwards, we keep on overshooting the minimum again and again. Here also, notice that the learning rate is fixed. So the length of each iteration will actually depend on the magnitude of the gradient. So here you see that in step 4, the magnitude of the gradient is quite small. So this step 4, from 4 to 5, this step is small. But in step 5, the magnitude of the gradient is larger. So from 5 to 6, the step is larger. And in step 6, the magnitude of the gradient is very high, because here the tangent is very steep. So from step 6 to 7, this step is quite large. And from here, we can see that here it reaches a situation where actually the gradient descent algorithm finds this saddle point here, this region here, as the global minimum. This is not actually the global minimum. As we can see here, x equals to 1.5 has the global minimum, but the gradient descent algorithm finds that in this region it is appearing to be a minimum, and it is taking this minimum to be the global minimum, which is not true. So here we see that with this learning rate of 0.4, we are not really reaching the sought after minimum. Yes, exactly. And it is not really just because of the flat part, but in any function, there could be a global minimum as well as some local minimums too. So in case there are local minima, there is always a chance that the gradient descent algorithm gets stuck at some local minima, because after all, a local minimum is also minimum. A gradient descent is supposed to find a minimum, be it local or global, but our objective is to make the gradient descent work in such a way that it finds the global minimum. So that is where this learning rate term comes important, because learning rate helps us to find the global minimum. When there are situations where there is a possibility of this gradient descent algorithm getting stuck at a local minimum, we need to adjust the learning rate. The learning rate is static. We are not changing it. Before running the algorithm, we have specified the learning rate to be a fixed value, which we call hyperparameter, that is specifying some parameters before the model is trained, and we do not use those parameters while training. So learning rate is a hyperparameter, and we are not really changing it, but there exists some techniques where the learning rate changes dynamically with the gradient descent. There are ways the learning rate itself changes with the value of the gradient descent, such that it can help the algorithm go find the global minimum instead of the local minimum. Here we have a graph with a comparative study of what this learning rate should be. Obviously, this gives a very approximate notion. It is, you can objectively say that how high is very high, how high is high, how low is low. So this is a very ambiguous thing actually. There is no definitive value to saying low or good or high or very high. You have to try it out. But in general, this is the trend that we see, that we say learning rate is good when, with the number of epochs, where we will come to what an epoch is, when with the number of epochs the loss function gets minimized. The number of epochs is actually the number of times the entire training set is trained on the model. So as the number of epochs, or as the training increases, we can be certain that the loss gets decreased. So with a low learning rate, it will take much more number of epochs or much more training for the loss function to be minimized. A good learning rate can rapidly uh, make the loss function come down with a reasonable number of epochs. A high learning rate may saturate the loss function at some point, after which the even after uh, hundreds of epochs, the loss function will almost static, and it won't really go down much. And a very high learning rate can actually backfire on the model, with, as the number of epochs gets increasing, the loss function actually goes upwards. Like uh, in this case, the global minimum is here, and after iteration 4, we can see that we are gradually deviating from the local minimum. So this situation is intuitively given by this very high learning rate. So is it clear till now? Yes, definitely. We can say that process always does not lead to the global minima as shown from this graph, because as I'm emphasizing again and again, we do not know how the function looks like. We do not really know how the function looks like, and that is precisely why we need to experiment with the learning rate. We don't know what learning rate is ideal, and actually if you go on with some hands-on training, you will probably see that probably a fixed learning rate is not very much ideal for any given model. As I've said earlier, there are techniques to improvise on the learning rate too while training, so that we can go to the global minimum instead of the local minimum if such a situation arises. Next, we go on to forward propagation. This is where we broadly go into neural networks. And before that, till this learning part, it was mostly uh, dealing with machine learning. Now we go on with something that is not really very much specific to machine learning, but with deep learning. So, what is forward propagation? Um, in machine learning too, when we start off, or in general, uh, we have some given parameters, and then the model runs on those parameters. We have some inputs, then the inputs along with the parameters get some function onto which they do some calculation. That function is called the activation function, and then it gives the output. So this happens in a neural networks uh, from one layer to another. So this is what basically called forward propagation. It refers to the movement of the input through the hidden layers to the output layers. Uh, so we can say that in forward propagation, the information travels in the forward direction only, and there is no backward movement of information. The input layer supplies the input to the hidden layer, and from the hidden layers, the information is gradually transmitted to the output layer. So this is what is forward propagation. It's an easy process. Now we come to backward propagation. This is a very important process which needs a lot of attention. Back propagation is mainly where the learning in deep learning or in machine learning takes place. So, what is back propagation? Back propagation is a mathematical term. It is precisely speaking an algorithm for calculating the gradient of a loss function with respect to the variables of a model. So backpropagation is essentially an algorithm to calculate the gradient of the loss function. In this paragraph, as I've written, maybe I should zoom in a bit. Let me read this out. When we define a neural network, we assign weights and bias values to our nodes. We do this at the starting of the training. Then once we have received the output for a single iteration, we can calculate the error of the network, the error or the loss. This error or loss is then fed back to the network along with the gradient of the cost function to update the weights of the network. These weights are then updated so that such that the errors in the subsequent iterations is reduced. This is essentially what happens when we say the machine is learning. So in this process of updating the weights using the gradient, using the gradient of the cost function, this is known as the back propagation process. So there is one distinction that we need to know. Sometimes we use the word back propagation in a very loose sense, but it is actually a very mathematical term to refer to algorithms which are used for calculating the gradient of the loss function. Here is one simple neural network where it is illustrated how forward propagation and backward propagation takes place. Here the signal propagation direction is actually the forward propagation. Here the error back propagation is shown, and the here in the middle two layers, these are what we call the hidden layers. The circles are called hidden nodes, the squares are called input nodes, and this last one is called the output node. So the arrowhead in this diagram, shown in dark black, is towards the right. This shows forward propagation, and here we can see what backward propagation intuitively looks like. Here, once we have a set of training examples, we have in the here we have some inputs. We have some weights on which the input will add on to give the outputs of the subsequent layers, and then finally the predicted output of the output layer is given. But as it is, the output will not be very precise in the beginning. In the green circles here, it is shown the difference in the desired values, like what the model should expect to show to predict, and the model and what the model is actually predicting. So we take account of the loss here, and then we propagate the loss with help of the gradient descent and back propagation algorithms right through the hidden layers till the input layer. So in this back propagation process, what we do is we update the weights so that in the next iteration we can get uh, output. We can get an output which is closer to what we might expect from the model. Here I wanted to emphasize on some of the misconceptions we have regarding back propagation. The term back propagation is misunderstood as meaning of the whole learning algorithm for multi-layer neural networks like these. So what really happens during this learning is that actually, since, as I had said earlier, backpropagation refers only to the method of computing the gradient, while another algorithm such as stochastic gradient algorithm is used to perform the learning using this gradient. And what do we mean by learning? By learning, we mean upgrading the by learning we mean updating the set of weights. The learning in machine learning actually refers to this updating of the weight parameters, because when we start off with a model, the weight parameters are are certainly not the ones we want. They are set at random at first. Then in this process of learning, we gradually get the set of parameters which will most ideally uh, give an output which is the closest to the outputs that we would want. So what we when we say back propagation as a process, we actually mean two algorithms working hand in hand. The first one is the back propagation, which is used to compute the gradient, and the second one is the stochastic gradient algorithm, which uses the gradient which is calculated by the back propagation algorithm to update the set of weights. So back propagation and stochastic gradient descent together helps the model to learn. And another common misconception is that backpropagation is often misunderstood as being specific to multilayer neural networks, but in principle, it can compute derivatives of any function. So, as I had said earlier, since backpropagation is actually a very mathematical term, it is precisely speaking an algorithm for calculating the gradient of the loss function. It can compute gradients of any function. Is it clear till now what the backpropagation process is really about? Hello, guys. Okay, I guess it's clear. Um, so I'll move on. Uh, Here are two terms that you need to know in machine learning. The first one is what we call a batch. While training a neural network, instead of sending the entire input in one go, we divide it into inputs of several chunks of equal size randomly. Training on Training the data on these equal sized batches makes the model more generalized as compared to the model built when the entire data set is fed to the network in one go. So this is something that has been observed while training machine learning models, that if we send the entire input in one go, the effectiveness of the training is not comparable to uh, when we divide the inputs into several chunks or into several batches of equal size and then feeding the model with one batch after the other. So training a model with batches improves the performance of the model with the given set of training examples that we have. And there's another term which we call epoch. Epoch is defined as a single training iteration of all the batches in both forward and back propagation. This means that one epoch is a single forward and backward pass of the entire input data. So in one epoch, we actually train the model on the entire training data set we have. The number of epochs that we would use to train our network can be chosen by us, of course. It's highly likely that more the number of epochs, the higher would be the accuracy of the network. However, it can also take longer for the network to converge depending on the complexity of the model itself. And also, we should also take care of the fact that if the number of epochs are too high, then the network might overfit. So this is where we come to another term which we call overfitting. So are we clear till now? Okay. So what is overfitting? In overfitting, this occurs when our machine learning model becomes really good at being able to classify or predict on data that was included in the training set, but is not as good at classifying data that it wasn't trained on. If the validation metrics are considerably worse than the training metrics, then it is an indication that our model is overfitting. There are many methods to address overfitting that we have given here. I'm not going to elaborate on these methods right now because it will take a lot of time, and you also need some prerequisites to go on learning with these methods. So the first method is simplifying the model. This is very much intuitive. If the model is too complex, then there's a high chance of overfitting. Simplifying the model often solves the problem of overfitting. And then there are other methods like early stopping, data augmentation, regularization, and dropouts. You can take a note of these methods, and then after the session, when you get some free time, you can search up on these methods. It is interesting to search up on how these methods actually function. Uh, then we come to underfitting. Uh, Underfitting is a scenario where a data model is unable to capture the relationship between the input and the output variables accurately, generating a high error rate on both the training set as well as the unseen data. So when does it occur? It occurs when a model is too simple and it is easily detectable. Why is it easily detectable? Because obviously the rate is quite high in the training set itself. So while training, if we see that the error rate is high, we can straight away say that the model is underfitting. And addressing this problem is also simple. Train for more time or use a more complex model for more feature extraction. Because uh, in underfitting, the model is not able to capture the features that we are giving as input. So either it takes more time, or rather it takes more number of epochs or more training for the model to learn the features, or maybe we need a more complex model to learn more features, because maybe our model is too simple to extract the features that we want the model to know about. This is an illustration of what an optimum function should be, what overfitting looks like, and what underfitting looks like. In the left, we can see that this function is underfitting. Why? Because it has a high error rate on the training set as well as the testing set. In the right, it is overfitting because it has a low error rate on training set but a high error rate on the testing set. And in the middle, the function is optimum because the training error as well as the testing errors are quite low. So it is not that in the optimum model, the all the predictions will be pitch perfect. There will always be deviations, but the deviations will be such that the overall error rate is minimal, both from the training as well as the testing set. This is a graph showing underfitting versus overfitting. Um, here, we here we see that as the number of epochs is increasing, for a model which is underfitting, the, the training error uh, the training error will be high as well as the testing error will be high. So here, as the model is trained 20 times, we see that the training error is small and the testing error is small. So we can say that at this position, the model is just in a right state to be accepted as a good prediction model. If we go on training for much more epochs, like say for 100 epochs or more than that, the model will gradually overfit to the data. The training error will go down, but after a point, the testing error will gradually go up. So this is where we say that the model is overfitting. So in this region around epochs 1 to 10, we can say that the model is underfitting because the amount of training has been under optimal. Around epoch 20, the model is optimally trained because the training error and the testing error is small. But after that, we can say we can see that the deviation between the training and the testing errors is gradually going up. So after this point, we can say that the model is gradually overfitting. This is a model complexity graph which is showing more or less the same thing. In the region with a small number of epochs, we can say that the training error and the testing error both are high. Here, in this region with the orange circle, we can say that the model has been optimally trained because the gap between the training error and the testing error is low, and both of them are are almost at the minimum. But after this region, we can say that even if the training error is going down, the testing error is actually going up. And the characteristics of a good model is that the training error and the testing error both should be low. It's not only that we will say that the model is overfitting when if only the deviation between the training error and the testing error goes up. If the training error is also high, but the deviation between the training error and the testing error is low, we don't say that the model is optimally trained because the training error is still not very low. It is still not as low as we would have wanted it to be. Um, So this is all of today's session. Are there any doubts? Okay then. We may leave now. One key takeaway from this that this concept of back propagation, that back propagation is not really a process, it's a mathematical algorithm for calculating the gradient of the loss function. And back propagation along with optimization algorithm is used to perform the learning in the machine learning module. So this is all about today's session. Are there any questions? Okay then, we can wrap up now. Thank you.